Hi, I'm Po-Yu Lin from New York University. It is my great honor to present P-KNN, a framework that jointly calibrates multiple pathogenicity prediction tools. We have many computational prediction tools that assign a score to each variant, predicting whether the variant might be pathogenic. However, to make these scores clinically meaningful, we need to map them onto pathogenicity probability according to guidelines. This process is called calibration. The current calibration method uses a calibration dataset with labeled pathogenic and benign variants. And for each score, we look at nearby variants within a window and estimate the pathogenicity probability with the fraction of variants within this window that are pathogenic. However, current calibration method can only use one tool at a time, preventing clinicians from using multiple tools with complementary strengths. This is where P-KNN comes in. The idea is simple. Instead of using a one-dimensional window for a single tool, we extend this into a multidimensional space where each tool defines a dimension. Then, for a covariant, we find its nearest neighbors in this multi-tool space. And just as in single-tool calibration, we estimate the pathogenicity probability from the proportion of pathogenic variants among its neighbors. Since different tools may be on completely different scale, we perform a ranking normalization of each tool's score. In addition, since each tool differs in their ability to discriminate between pathogenic and benign variants, we scale the score of each tool by their mutual information with pathogenicity labels. We evaluate the performance of a method on a held-out test dataset using two metrics. The first is evidence strength, which measures how much the posterior probability differs from the prior, expressed as a log likelihood ratio. The larger this value, the stronger the correct evidence is provided. The second is calibration. Here, we group the posterior probabilities into bins and compare them with the actual proportion of pathogenic variant within each bin. If the curve falls below the diagonal, that means the posterior probability was overestimated. We apply P-KNN to 13 commonly used prediction tools. Compare with the best 4 tools within these 13, P-KNN achieved a stronger evidence. At the same time, the calibration from P-KNN is excellent. By contrast, the individually calibrated tools frequently show regions where probability is overestimated. Because P-KNN is a flexible framework, we tested how it performs over time, using only the tools available at 4 different historical time points. As new tools are incorporated, the evidence strength of P-KNN gradually increased. In fact, with the latest set of tools, P-KNN outperformed alpha missense, which is the strongest simple predictor today. And importantly, across all these different combinations, P-KNN consistently maintains good calibration. To summarize, P-KNN enables joint calibration of any set of pathogenicity prediction tools. It produces stronger and more reliable evidence than individually calibrated predictors. And it can seamlessly incorporate new tools as they emerge. Thank you very much.